to the cloud. Okay, perfect. If you just want to come over here, or you can be on the screen. Okay, guys, we're gonna get started. Thanks for coming to the review session. We hope this is helpful for you. We are recording it, so this will be posted to Learning Suite after. Couple announcements. Like Jocelyn said in class, this test is open note, open book, open internet. It is not open AI, so no AI usage at all, period, right? So you can, use resources online, but that does not count AI. So yeah.
Every time I Google something, I get an AI response.
That's a good question. Yeah, that's a good point.
That's different than ChatGPT, though.
I think
that's
more
like a summary of what comes up.
Yeah.
Yeah, I think that's
sometimes
totally.
I'm like, what's this code for Stata? And then it like writes the code in the thing.
Right. So yeah, that's the kind of question I wouldn't look up online. I would, when she says open internet, it's kind of more like if there are resources on the internet, for example, on Learning Suite, you can access those in the content tab. You can look up Stata guides and then look that up, right? Or like websites that have information about assumptions, things like that. But just typing in the question into Google, avoid that. Does that make sense? In addition, I can't turn off this audio for some reason, so I'm like hearing myself talk a little bit. Yeah. In addition to that, once the exam opens at 2 p.m. today, you can no longer talk about it with anybody, including us. Okay, so any questions that you have about it, ask within the next hour when we're going through it. Okay. Yeah.
You ask questions after if you have an exam after this?
Not until the exam closes.
Wait, like even if we're in this room and I haven't looked at the exam and we have just.
No, that's fine. Yeah, sorry, I meant
while we're this.
While we're here, it's fine.
All of your. It's like, oh my gosh.
No, sorry, I thought you meant after you're done with the exam. Yeah, even after you like finish and you turn it in, you still can't talk with your other classmates about it until the period closes, the exam period. Sometimes there might be like questions that come up as you're taking the exam, like I don't know, technical difficulties or something. If something happens, yeah, if you have a question like that, that's not really about like exam content, email Jocelyn and she will have the discretion to know whether she wants to respond to that or not. But I remember, I think the first midterm exam I think I had one like minor question like that or something, and I emailed her and she responded. So field those questions to Jocelyn, not us, if you have them, because she can make that choice of how she wants to respond. Yeah, and then on the test, there will be some instructions at the front. One of the points I think is really good to mention on there, it talks about like if you don't understand the wording of a question or if it's not super clear to you, give it your best guess at what you think it's asking, and in your answer, tell us what you think it's asking and answer that question, if that makes sense. Like give us every reason to give you points. So show work. If you don't understand something, explain what you think it is and answer it, and we'll take that into account. Like we are not trying to give you low grades, so give us every excuse to give us. Yeah, give us every excuse to give you points. For the long answers on the test, you do need to show your work to get points. For the short answers, you don't need to, but we recommend showing work so that we can give you more points, even if the answer is wrong. So what we're going to do is we're going to go through this practice exam, which is on Learning Suite. What did you title it again?
I think it's just midterm 1 practice exam, but then it says like review session or something in all caps next to it.
Yeah.
Something like that.
Yeah, so it's in the content on exam prep if you want to pull it up. We're just going to walk through and each question and kind of show you how we would answer it. This will help a ton with the actual exam. And then just ask questions as we go along. Okay, so Hannah's going to start. And I'll be back.
Could I just...
You're good, just keep it.
Perfect. Awesome. There's one more thing I was going to mention, which is that there is a class that comes in at 2. And so there may be a few questions that we don't have time to get to in this review session, not necessarily from the test, but if you're asking questions that I feel like could be explored outside of this room or that aren't relevant to the test content, I may kindly ask that we keep going just so that we get through everything before the next class comes in, and then I'll still answer your questions out in the hallway or whenever I can. So awesome. So this first question requires you to explain what is meant by holding all else equal in a multiple regression framework. And I don't know if anyone wants to give this a stab, but what this is referring to is that when we're conducting multiple regression, then we hold anything in the error term constant that we think might be correlated with our main X or explanatory or independent variable. And so I can write this down. But this refers to all other X's in the model being held constant. And the way that you hold things constant in a model is by including them as controls. That's how you pull them out of the error term and make sure you're accounting for them in the model, so that they're not influencing your dependent variable without you being aware of it. I think that would honestly be sufficient for that question. Do you have any follow-up questions on that? Okay, I'll keep
Conversation about this part, sorry. Like, do we need to write down like how to do it?
I think that what I have here would be sufficient. So Anna asked if you need to explain that you would include those X's as control variables. I feel like that would be relevant information, but if you didn't include that, that wouldn't necessarily mean that you wouldn't get points. So,
Okay, thank you.
Number 2, what are some descriptive statistics that show the relationship between two variables? Does anyone want to call some out?
Correlation.
Yeah, a correlation that tells you the strength and the direction of the relationship, even though it doesn't tell you the slope of the line. So that would be really appropriate for a preliminary analysis. Another one that you, I think you did this in your most recent problem set 3, where you looked at wives' levels of depressive symptoms at high and low levels of mindfulness. But even just looking at means and comparing group means can give you a lot of information about what patterns are going on in the data. And so that would be another option that you could put here. Those are the 2 main ones that I can think of. Do you have any others that you want to call out? This would be sufficient to answer this question. Comparing group means can be especially helpful as a form of preliminary analysis if you're doing an analysis with a moderator, because a moderator essentially looks at that relationship between your independent and dependent variable at different levels of the moderator. So if any of you are using moderators in your personal projects for this class, I know that Jocelyn does require you to do preliminary analyses for your paper. And so comparing group means would be super relevant for you.
Another one too, scatter plots. That's another one we've done.
Yeah, that's true. Scatter plots would also be awesome.
Like knowing. Oh, I guess standard error.
No, it would just be like any type of analysis that you would run to pick up on a basic pattern preliminary to running your regression. So, yep. All right, so I'll read this next one. One of the Gauss-Markov assumptions is that the errors are mean independent of the explanatory variables. Meaning that the errors and the explanatory variables or variable are not correlated. Give a real-world example of a dependent variable and explanatory variable where you suspect that this assumption would be violated and the errors would correlate with the explanatory variable. Explain why you think the assumption is violated. I think you also did something like this in problem set 3, and I did leave feedback on that question for this specific reason. I think it was asking about, it was looking at mother's education as the independent variable, and then birth weight of her baby as the dependent variable. And we asked you what other types of variables might be contained in the error term that are influencing that dependent variable of birth weight. And then we asked you to identify which of those listed variables would also be correlated with your X or dependent variable of mother's education. Those would be the ones that you would want to pull out of the error term and include in your model as controls because they're correlated with both your X variable, your explanatory variable, and your Y or your dependent variable. So another example I can think of yeah, that's true. And then instead of writing it,
This
Yeah,
one you'll probably
that's
write
totally
more of a
fine.
paragraph if you get this kind of question, but we won't make Hannah do that.
okay, I won't write a paragraph, but I'll do like a brief example.
Out of curiosity, are you guys sharing your screen? I don't know if you are.
Yeah, this is, so this is showing Hannah's computer. This is showing Zoom on Hannah's computer.
So this is what the recording will be of, is
Is this,
of the
so
iPad.
you'll see it. Cool.
I'm writing way too big for this, so the equation will spill out, but let's say that we are looking at child behavior problems as our dependent variable, and then we want to know how this is predicted by parental monitoring. So some things that I think might also predict child behavior problems might include child temperament, or maybe parent mental health, or SES. And I could see ways, or can think of ways, that all of these might be correlated with parental monitoring as well. For example, if a parent has low SES, maybe they're spending more time at work, and so they are monitoring their child less, but then that low SES might also affect child behavior problems directly. And so that might be something that we pull out of the error term, which would be over here in the equation as well. That might be something that we pull out of the error term and include as a control, just because we don't want our error term to be correlated with the X's. And we could go through that same process for parent mental health or child temperament, but I think that suffices as an example. Do you have any follow-up questions on that one? No? Okay, I'll keep going.
Just don't use Hannah's example if you get a
Yes,
question like this.
don't use my examples, or like, we'll know if you worded things the exact same way that we did on this,
So you can use
exam.
this as a resource, but
yes.
use your own example. Like,
Think through your own examples and word things yourself.
we do it if it's from homework.
I don't know, that's a good question. I would say probably think of an original example just because you can. And we forget.
Yeah, we can make that right now
Yeah.
if you want. Just
Yeah.
come up with a new
Come up
example.
with a new example.
Show us you understand.
Awesome. And then number 4, consider the simple regression model with population y equals beta naught plus beta 1x plus e. graph the true relationship between X and Y, label one of the errors, and then graph the estimated relationship between X and Y found using OLS and label the predicted error or the residual. So I think Jocelyn was pretty good about like drawing this multiple times for us in class. But let's say that this is the true relationship, or our beta 1 or beta naught plus beta 1 X. And then we would also have our, well, I guess I can label this one first. So this is the real line that we never see. Sorry, my handwriting isn't the best on this. No, it's okay. No, I like it. I'm just not used to it. So that represents the real line that we never see. And then let's say that this line, this is our predicted line. So the equation would be the exact same, except because it's our best guess, then we have the little hats on here. So that's our guess at the line. And then we're just going to draw a random data point here. Oh. And this would represent the residual, is the distance between the data point and the predicted line. So that would be BI hat, because it's our best guess at the error, but this is also called the residual. And then our true error would be represented by the distance between the data point and our true line, or the line that we never see. And that's what you would draw for this problem. I think that's pretty comprehensive. I don't think I'm missing anything. True relationship, label one of the errors, and then the estimated relationship. So that's what you would draw for that problem.
So is it gonna be best for us to print this test into a gallery rather than?
Yes. I highly recommend printing it, and then you can either scan it or just take pictures to upload.
Or you can use a separate sheet of paper for your answers and just write it on down.
Yes.
Those instructions will be on the first page of the test. She has like a note that'll say like, you can print it if you want. If you don't want to, you can just use a plain sheet of paper and number your answers.
Yes.
And show your work there.
Either is great. And then what was your question, Jenna?
Just for the error for like the real population line, is that like also considered a residual, or is that just like the true error?
That's just considered the error, and then our best guess at the error is considered the residual. And yeah, go ahead, Lainey.
I just was wondering, does the estimated line always have to be like horizontal?
No.
Okay.
It just totally depends what the slope of your line is. So that was just a random line that I drew, but it could have gone in any direction. Yeah, Robert.
Can we draw and write in Word if we want to, or is that like?
Yeah, if you're like confident doing that, I know that would take me a lot longer than just drawing things out, but
If
yeah,
you have an iPad
totally.
and you want to just.
Or if you have
draw
an
it out,
iPad, yeah,
whatever.
whatever works best for you individually is totally fine.
Okay, we need to move
Awesome.
on. All right. So moving on to number 5. Okay, when estimating a bivariate regression model, what is beta naught hat? Does anyone know what we call beta naught hat? The intercept, that's right. What about beta 1 hat? The slope, yeah. And so I might put something here like beta naught hat is our y-intercept, which I would clarify what that means, right? It's the value of y when all the x's are 0. Beta 1 hat, just like you said, we would want to say that's the estimated slope. Yeah. The estimated slope of the relationship between x and y. Yeah, I might talk through a little bit and then write, because it's easier for me to say than then write. But I will come back here as well. for you guys. Any questions about slopes and intercepts?
Should we be putting like hats over the Ys and X's in this situation? Does it matter all that much?
No, not for the X's. It's a good question. What's another way to talk about that slope in terms of units of change? Yeah. And in other words, we could say our slope is how much y would change if x changes by 1 unit. So that would also be a good answer for what. Okay, what is the conceptual difference between the population unknown parameters and the estimated parameters? Anyone want to take a stab at that? What's the difference between the population and our sample parameters? The ones that don't have hats and the ones that do.
Well, the sample's just based on the participants in our data, so it's gonna change based on which participants are in your data, how big your data set is. And the unknown parameters are what the true thing is that we don't just won't ever know.
Exactly. That's perfect. So here I could say something like that is my answer. That's a great answer. Could say something like the population parameters are the true relationships, right, in the true population. But those are never known. They're never observed. We can't see them. We can't figure them out. And our estimated parameters, just like Kara said, are from the data from our sample. We use those to make guesses about those parameters, those real true parameters. But we can never actually know them. Any questions on population versus sample? For the sake of time, I'm not going to write out that answer, but when you're taking your exam, if you get a question like that, you'd want to write out just kind of like in short paragraph form your explanation of that. Like what Tyra said or what I just said, just kind of explaining what definition. Okay, homoscedasticity. Does anyone remember what that means? This is one of our assumptions of linear regression.
The variation is the same, it's constant.
Yeah, variance of what?
Variance of the data points.
Yeah, of the errors of the data points, right?
okay,
Which will look, yeah, it'll be basically the same thing. And so that's one of our assumptions of linear regression. We want homoscedasticity. Heteroscedasticity would be the opposite. The variance of our errors are changing based on our X value, right? So I'll show you an example of how you might answer this question. This is just drawing a picture, right? So we draw maybe 2 axes and our estimated line. For homoscedasticity, this is when the errors do have constant variance. It might look something like this. The errors of each of those data points are about the same because they're kind of a constant distance from the line. We're not seeing like a fan out. Versus in heteroscedasticity, we see our data points, they'll fan out because as our X value changes, they could fan in or out. So this is just one example of what it could look like. Maybe down here for these lower X values, they're pretty close to the line. There's smaller errors. Oops. But as the X value increases, you see how we kind of get this fan effect. Our errors are growing. Okay, so that's heteroscedasticity. And we kind of have that fan effect, and it could go either direction, maybe with your lower X values, your data points are more spread out and then they kind of thing. Moving on from that one, in a multiple regression model, what is R squared? And what is the range of R squared? Anyone want to take a stab at that question? What does R squared mean?
It's how much of the explanatory variables explain the changes in the dependent variable.
Yeah,
And it's gonna be like 100%, so it just.
Yep, 0 to 1, yep, so we can say R squared is the percentage of the variance in Y that is explained in our model. Or by our model. You're welcome to put more detail than I am right now, but for the sake of time, I'm being short-handed, but another way to say that Y, like the percent of variance of Y that's explained by our model, is the percentage of variance in Y explained by all of the X's, all of the predictors together. And you're right, the range is 0 to 1, which is the same thing as 0 to 100%. Right? So it's a percentage of how much of Y. So based on that, what do you think? Which value of R squared indicates a better model fit? 0.05 or 0.85? That would be the same as 5% and 85%. Which one is explaining more? Yeah. It's a higher percentage, right? More of our Y is being explained by the model. Okay, any questions about any of those concepts so far before we move into our long answers? Okay. All right, let's keep going.
How many questions are there?
In this practice exam, there's like
They're all numbered like
8 short response and there's
each
3
section,
long.
so
Okay.
We have not seen the exam for this year yet, so we cannot confirm how many, but
it'll be
this-
about this length.
yeah, this should help you quite a bit.
I can always count them up. Here.
Yeah, you got one.
I can count them.
All right, let's move on to interpreting our data output. So this whole long answer question here, number 1, is worth 15 points. And it has a few different parts. Okay, I'm gonna skip this paragraph here because it's just telling us what the variables mean, but when you take your exam, you'll want to read through that and make sure you understand what all these variables are representing.
It looks like there are 22 different items, but a lot of the questions are like sub questions that you're answering regarding like one set of data output or something bigger like that. So yeah. So yeah.
I don't know if this is better now or at the end of the review, but I would love to go back through the assumptions we're making right now.
Yeah.
Yes,
Okay.
that will
We have
be,
that
there's a
standard.
question about that, so we'll get to those.
Yep, great question. Okay, so we're gonna look at this output and practice interpreting it, okay? So here's our code that, here is our code that was put into Stata, my hands. And then here's our output, right? Like we've gone over before, for our output, we have a few important pieces of information. We've got our sample size over here. We've got our R squared here. And then we mostly want to look at this table here for our interpretation of our regression. So, just looking at the code first though, that reg, sex, frequency, wife, and bar wife. Bar is the, it's the Bayer attachment scale, so we'll call that wife's attachment. What's our dependent variable and what's our explanatory variable? Okay, how do you know that?
It's first.
Yep, exactly. We always put our dependent first, right? And so that would make our independent or our explanatory variable wife's attachment, right? I'm not gonna write that there, but that's all you would write. Dependent variable is
Can
blank.
we write the
Mm-hmm.
short version of the sex-free W?
Yeah,
Yeah, that's
that's
fine,
good.
as long as we can tell that you have identified the correct one.
Yeah, so you could write like bar W. You will have to interpret later what that is. Okay, let's write out the linear equation. So let's use just our general linear equation here. We've got yi hat, I means individual, right? equals our beta naught hat, which is our intercept, whoops. Plus our slope, which is always attached to an x, plus our error. We won't do anything with the error, but I just like to put the error because it's there conceptually. We're not gonna fill anything in for that. Yeah,
Is that an I next to X or one?
that's a 1. Sorry, my eyes are curvy.
Okay.
My ones are, should be straight. But it's not. Good question.
Are we supposed to be putting the real numbers in there?
Yes,
The
so I'm just drawing this first,
okay.
yep, just to show you kind of the general structure.
Why are some of them one?
Yeah, so, honestly, you can ignore that for this. Actually, no, you shouldn't ignore that, that's important. So 1 as a subscript just indicates this is our first predictor. This is our first X value in our equation. Since we only have 1, you only have 1. But if you if we had a multiple regression equation here, just like we've seen in class, you might have like a second slope here for your second predictor. Does that make sense?
Yeah.
So the subscript of 1 is just to indicate this is our first predictor. Yeah. Not in this class. In the future, you're probably be fine with it. Yeah, it's a bit different when you get to multi-level modeling, but you don't have to worry about that right now. Yeah. Okay, so what will we fill in here? Okay, so what's our y? You know, it's our sex frequency of y's, right? So we'll put that in as our y equals. Okay, looking at the output, what's our intercept?
We're 3.5.
Yep, correct. Yep, so we plug that in. What about our slope for attachment? 0.5. 0.50. Is it positive or negative? Yep, so we put plus, not minus, right? And then we want to attach it to our x, which is our
Attachment for.
yeah. So you could either write wife's attachment, you could write bar W. And then you don't need the error term for this. Okay, so that's how we would write that equation. And so that's what your answer for that question is.
The hats over, like you put the hat over the dependent variable, we need to put that
Yeah, you
over
could,
all of them, or again.
I don't know, what do you think? You could put it over the X.
Honestly, I feel like statisticians are inconsistent with it, and so you guys can be too. Technically, my personal
Technically, you
feeling.
could do that, but I've never seen Justin do that, so.
Yeah.
You don't need it.
In the actual equation that you've already plugged in your numbers, you don't need the hats.
Okay. So if we were to interpret this predicted relationship, what would we say? I'll go back up to the output. How would we interpret this relationship between wife's attachment and wife's sex frequency?
Sex frequency goes up in 1 unit. The attachment of wives bar W goes up 0.50.
Close. You've got those two reversed.
Okay.
But
Reverse
you
that.
got it. Yeah, good job. Is because our independent variable here is our attachment, right? So as our attachment increases by 1 unit, a wife's sex frequency increases by 0.5.
Because that's the predicted.
Right? Yeah. What would we say about that relationship between the two variables? What would we call that relationship? Or that correlation?
Significant positive.
Yeah. You don't have to talk about significance in this question. It is a significant relationship there, you can see from the p-value. But what you do want to include in your interpretation is what Kyra just mentioned. So we want to say that a wife's sex frequency is positively related or positively correlated to her attachment, right? We know that because as one goes up, the other one goes up.
And what about the effect, like the magnitude, is 0.50 high?
That's a great question. Right now you don't have the scale information, so you can't deduce that from just this output. So you don't have to talk about magnitude on this. Actually, we will in a later question. But that's a great thing to be thinking about. Every time you do talk about a relationship, you're gonna want to go back and look at your scale and be like, how big is this change? Yeah. But for this, we'd want to say that there's a positive relationship And just like Kyra said, as our independent variable goes up by 1 unit, our dependent variable changes by how much. And then it says relate this to family studies and explain why this is an unexpected or expected finding. I'm not gonna go over that because we are rapidly running out of time. But you'd use your own intuition here and just explain, like, does this make sense to you? Does it not, based on what you know about family studies? Does it make sense that a wife would have more sex with her partner when she has a better attachment? And explain why, right? Okay. Now it's asking us, what is the predicted level of sex frequency for a person with a score of 4? Okay, so what we're gonna do here, this is just a simple math problem. We're gonna go back to our equation, so you'll just end up like copying the equation you wrote earlier, and we're just gonna plug in our numbers. Okay, so if x equals 4, we'll plug it in and do some math.
Love you too, right?
Yeah, 0.5 times 4 is 2. We'd add that to 3.52, and what would the answer be? 5.5. Perfect. That would be your answer to that question. That one's just a simple plug into the equation and tell us what you get. Show your work. Okay, if you just have a number there, you will get points off. Because for those long answer questions, it requires you to show your work and you got it. Okay. All right, here's another regression. Looking at this one, what's different about this one compared to the first one? And don't think too hard on this.
Yeah, there's an extra variable.
Yeah, it's a different variable, right?
Their husband, it's about the husband.
Exactly. That is the answer here. You would say more than just the word husbands, but yeah, basically this output is for husbands, while the first one was for wives. Don't overthink that question. Okay. And we can tell because there earlier in the question it told you what each of these variables are. Okay, interpret the differences in the slope parameters between the two regressions. Explain why this is expected or unexpected. Okay, so this is going back to Lainey's question about magnitude. Okay, so let's look. Here's our slope for husbands. And again, this is the slope for attachment predicting sex frequency. Okay, so for husbands, we've got 0.43. What was our slope for wives?
0.50.
Perfect, 0.50. Okay, so what would you say about the difference between those two slopes? Which one is bigger?
More important for women to feel attached to their husbands than it is for men in regards to having sex frequency.
Right, we would say there's a larger magnitude for wives, right?
We don't know for sure because they're not in the same model. It could be statistically.
That's a good point, right? Technically, you actually can't compare coefficients when they're run in two different models. For this question, we're just gonna think conceptually. But you're exactly right, Kyra. We would say in this one, I'm gonna write out what I have here because I think it would be helpful. The larger magnitude for wives suggests a stronger connection. Because that's really what we're looking at with magnitude. The size of our coefficient tells us how strong is the relationship, how big is it. It suggests a stronger connection between, I'm going to abbreviate here, but attachment and sex frequency for wives compared to husbands.
Which is a supported finding that we've learned.
Yeah, so for that second question, explain why or why not this is unexpected or unexpected. Tell us what you think. You don't need to know all the data about attachment and sex frequency, but tell us based on your own perception. Does that make sense? Why or why not? We'll accept either answer if you justify it. Okay, any questions about those parts? Make sure we get to what you guys. Okay. Okay, you got it.
Yes.
Okay.
We're gonna do a little bit of jumping around on these ones. So we're gonna talk for a second about the properties of regression or ordinary least squares regression models. And I'll just read this first question. It says, suppose you ran a regression and found estimates for the betas in the model. What is the distribution of beta 1 hat? Explain the connection between the distribution of the error terms and the distribution of beta 1 hat. And we know, this is kind of like I drew earlier. But we know that with regression, beta one hat or the slope is just a linear combination of all of these little errors. Kind of like I drew earlier. And we assume that these errors or the distance between each of these data points and that slope line, we assume that those errors are normally distributed. So this assumption that errors are normally distributed, because the slope line is calculated using the sum of squared residuals, or it's calculated using those errors, then we also assume that beta one hat, that distribution for the different slopes, we assume that it is also normally distributed. I'm gonna write this down quick.
And so that would be your answer to that question. The distribution of beta one hat is normally distributed. And when it's talking about the connection between the error terms and the distribution of beta one hat, we want to explain there, like Hannah said, it's because we know our errors are normally distributed, because that's an assumption of regression. And because our beta one hat is a linear combination of those errors, we know it's also normally distributed.
Is that the Gauss Markov?
So that's one of the Gauss Markov.
Yes.
Yep. And we'll go over that in the next question.
Another way to think about this too. Or at least this was helpful for me. I'm not really like a huge person when it, like a huge math person when it comes to like understanding the equations. But when you calculate the variance or distribution for beta one hat, you literally plug in the variance of the error into that equation, which also demonstrates that that distribution of beta one hat is completely contingent on knowing what the variance or the distribution of the errors are. So that's another way to think about it, if that's helpful for you. And then I'll let Julia go over the assumptions in a little bit more depth. And then there will be one more question about
For the
this.
sake of time, would you mind writing this there as I?
Yeah,
for sure. Okay, what is the Gauss-Markov theorem? There's an acronym that goes with it. You guys remember it? It's a color. Blue, yeah. So all the Gauss-Markov theorem is the OLS estimator is the best, which means most efficient, linear unbiased estimator, which is blue. Okay, she'll write it here. But what this means is that we assume that in the ordinary least squares method of linear regression gives us an estimator that has the lowest variance of any other linear unbiased estimators. Now, how is that different from the assumptions? The assumptions are just what we need to assume to support a linear regression model. And there's 4 of them that we'll review briefly. But that's really what you need to clarify is the theorem is telling us that the OLS estimator is the best, which again means most efficient for lowest variance, linear unbiased estimator. And the assumptions are a set of conditions that need to be met for us to run a regression. That's how you would distinguish between the two.
The way that I kind of like to remember it is that blue is true if the assumptions are met. And so the Gauss-Markov theorem or the statement that linear regression is the best linear unbiased estimator, that's only true if those Gauss-Markov assumptions are met.
Can you tell us the difference again?
Yeah. So the theorem says that the OLS estimator is blue, right? It's the best, most efficient linear unbiased estimator. The assumptions are the conditions that need to be met for blue to be true, for our OLS estimator to actually be the best, and for us to even run a regression. People are gonna be opening the door for the next 10 minutes, just ignore them. We have this room until 2, so we're good.
Yeah,
Okay,
we'll try to be quick.
we might have to save some of question 3 for a video that we will post for you guys to use on this. Okay, quickly reviewing those assumptions. Our Gauss Markov assumptions are assumptions 2 through 5. 1 through 5 we would call, I think it's like the linear regression assumptions or something. But our Gauss Markov assumptions are 2 through 5. So we have exogeneity, which means the distribution of the error terms and the X are not correlated. That's the question we were talking about way at the beginning, right? When Hannah was talking about choosing an example where we've got errors that are correlated with
It's the exact same as saying that what's in the error term can't be correlated with your X's or independent variables.
That's no.
That is, this is different.
that one's number 4, yeah. And then our homoscedasticity, we talked about that too, right? That our errors have a constant variance.
They're not fanning out.
Number 4 is that the errors are independent from each other. And again, when this is violated, there could be really 2 main ways that's violated. Autocorrelation, which is when we have the same person multiple times in our data set, so their errors are correlated with themselves. Or serial correlation, which is when 2 different people or more in our data set, their errors are correlated, which would be like husband, wives, families, yeah.
This is technically in a perfect world, right? Because we're gonna still run
Yes.
regressions even when things are correlated, because otherwise we just won't run anything.
Yes, some of these we can satisfy and some we can't. So like number 4, we can always satisfy that one.
Fair enough.
That's why we wouldn't have like a husband and wife in the same regression. We'd need to do SDM, which you guys will learn about next semester. 5 is always gonna be satisfied. This one is complicated to understand, but all you need to know is that the X's are non-stochastic, which means they're fixed.
Cool.
But yeah, you're right, like that first one, which isn't one of the Gauss Markov ones, but our distribution will not always be perfectly normal. We won't always be able to be perfectly exogenous, whatever.
That was awesome.
Exogenous, thank you.
And that's why we never say X causes Y, is because we can never fully meet these assumptions. That's why we say X is related to Y. Okay. All right, and that'll be recorded on the video if you want to go back and review those. Okay, what do you think, Hannah? Do you want to answer
I
this
just
one?
want to be really fast at that
Okay.
one, and then I'm happy to make a video for number 3.
And maybe we provide some time for a couple of questions.
Yeah.
Too.
That's
Okay, does
perfect.
that work for everybody? Okay.
What about the very last question? I remember looking at this.
Hi, and you guys didn't want to do the video.
Oh.
Like this number 3. Yes,
Okay.
I will make a
We'll
video
go over
going
it.
over that.
Yeah.
So really fast, is the OLS estimator consistent? Oh, I'm on the eraser. The answer is yes. And essentially what this means is that as we collect more data, then the estimator or beta 1 hat behaves in a way that is increasingly consistent or aligned with the true parameter. So like I drew earlier, we have our predicted line and then we have our true line that we never see. Essentially, what it means that the OLS estimator is consistent is that our predicted line gets closer and closer and closer to the true line with more observations or the more information that we have. Yeah, just what's in red here. And I think I'm trying to think, I was going to draw this out, but if you like think of a graph with just like an axis with just a few data points, obviously there are a lot more options for what that slope could be, as opposed to an axis where there are a ton of data points and that line can be a lot more specific or refined because we have more observations, we have more information to inform us of what that true line or slope might be. And I think that's about it. I do agree with Julia. It would be good to have time for a couple of questions. Do you have any follow-up questions either to that point I just made or just in general, things that you want to go over before we leave?
Just, sorry,
No, you can go.
I was just wondering regarding what you said, that the predicted line gets closer to the true line, the more data we give in the model. What if we add a variable that is not relevant? Like what we said in that case, if we look at adjusted R-square, it is taking into account the penalty, but if we don't, then it's not taking into account. Is that relevant to these questions?
Not as far as I'm aware. Because, yeah, not as far as I'm aware. I'm going to keep it at that.
This has more to do with the populated sample you're getting, and that has more
Not
to do with
reliable.
which variants you're using.
Yes.
Are we allowed to turn in the hard copy to you, or does it have to be,
Like
scanned?
submitted online.
Yeah, you have to submit it online. Sorry. I don't think, I'm trying to think of a way that you could reach us, but
I think I just submitted pictures, and if for some reason it's hard for you to submit pictures online or to scan your exam or write out your answers and then take pictures of those, I'm like more than happy to just, if you get me the hard copy before the deadline, I'd be happy to like take pictures and upload them for you even, but.
well, I just was hoping it didn't need to be in one document, because that you have to like pay to scan to put it all in one
Oh,
file.
yeah, don't worry about that, yeah. Yeah.
Like full ones that are free.
Yeah, I use Genius Scan, it's free, and I use that to scan documents and it keeps them all consolidated in one PDF. So I really like that.
Yeah, and feel free to submit multiple files and just name them what you want us to know which you are. If something happens and like you can't upload, just email us and email us pictures or something.
We totally get that technical difficulties happen and that you'll turn things in different ways, like just talk to us and we'll be accommodating.
Awesome. I think that's recording. So I just wanted to go through this last problem 3, that we didn't make it to in the exam review today. And it actually works out great because then I can show you my screen as I work in Stata. I think there will only be one problem on the exam where you will be required to work in Stata and turn in a do file. And then you'll also be asked to submit a screenshot of your output, I believe. At least that's the case with this example problem. But I'm just going to go ahead and open the do file and data file that I know I'll be using for this problem. We'll be looking at the relationship between child age and the amount of time that parents spend playing with their child. Let's see. There we go. So this first question asks us to create a table that shows how many minutes per day parents spend playing with children at these different ages. So of course, you could use the sum command to get means for the amount of time that an adult spends playing with their child at these different ages. And that output would just look like this. There would be your mean to plug into the table. But I also love this simple command, which is essentially telling Stata, give me a table based on age with the means for amount of time that an adult plays with their child. So I'm going to run this basic command, and that gives me my table with the different ages and then that mean amount of time spent playing with the child. And the next question asks that we explain in words what pattern we see in the raw data and whether or not this aligns with our expectations. So we can see here that between the newborn stage and a child being 1 year old, there's an increase in the amount of time that a parent spends playing with their child, which makes sense to me because I'd expect that a 1 year old is more capable of joint attention and interaction with their parent and just more likely to engage in play in general. And then we see that the amount of time that parents spend playing with children actually decreases with every additional year that that child ages after 1 year old. And this also makes sense to me just because children who are 2 or older may be more capable of independent play or playing with others and may spend more time playing with other people or on their own as they grow older. So I would say, yeah, that honestly does align with my expectations and the pattern that these preliminary findings suggest. That pattern makes sense to me. That's what I would say for B. And then estimate the following model using a linear regression. This is where you would include a screenshot of your data output. And I already have that syntax written out here with our dependent variable of the amount of time that parents spend playing with their child, and then child age, parent age, and the income of the family. Just going to run this regression. And then we're going to be looking down here at the beta coefficients in this first column. It says, interpret these findings in words, and then asks what those findings mean in context of our original research question, which I don't think it outlines the specific research question up here, but I'm going to assume that it is whether there's a relationship between child age and time spent playing with parents, just because that's what our preliminary analyses were focused on in these first two parts. So let's interpret these findings. We're looking at the coefficient for child age here as our primary independent variable. And what this indicates is that every additional year a child grows older, their time spent playing with their parent decreases by 4.19 minutes. I'm guessing it's in minutes. So that's what I would state here. And then what does it mean about the original research question of interest? I would say yes, this confirms that there is a meaningful relationship between child age and the total time they spend playing with their parent, because this p-value is less than 0.05. And I think the next question will go into this. I was going to say that aligns pretty closely with what we saw in our preliminary analyses with parents spending less time playing with children over time after age 1. I feel like I said that in a confusing way, but I can restate it here where it has us compare the results of the relationship that we found in the regression model with our raw data patterns. So yes, this shows that time that adults spend playing with children decreases as they grow older, and this preliminary analysis where we compared means for different age groups also indicated that parents or adults spend less time playing with children as they grow older. Of course, with this nuanced exception of between newborn stage and 1 year old. So I would state that, I would say yes, they do tell the same story in my mind. If you don't feel like they do, or if you would explain the raw data patterns or anything differently than I would, what really matters is that you can justify whatever answer you're giving. So demonstrate for us why or why not, in terms of whether they tell the same story. There isn't a right or a wrong answer. It's just a matter of your subjective evaluation of the data. And then part E, suppose you have a parent who is age 40, a child who is age 3, and then the family or the family has an income of $80,000. What is the predicted value for how much time they would play together each day? So we would plug these numbers in into our regression equation above. So let's scroll up. So the age of the child was 3. The age of the parent was 40. And the family income was 80,000. Just confirming that. Yep. And then you would also plug in these different beta coefficients and that intercept from your output. So let's find these numbers here. So it looks like our intercept is 49.4. So I would plug that in right here. And then our beta 1 coefficient is negative 4.19. I would plug that in here. Our beta coefficient for parent age is negative 0.16 that I would plug in there. And then the final beta coefficient for family income is 0.00015. So you'd plug that in right here. And after doing that multiplication and addition, you would arrive at the answer of 46.43 minutes each day. That's how much time an adult would be expected to play with their child if they were 40 years old and their child was 3 years old and their family income was $80,000. So I hope that helps with the last problem. Thanks for all of you who attended the review today. I hope it was helpful for you and good luck on your exam. Thanks.